Right now, you are spinning. Not slowly. Not gently. At this very moment, your body, your chair, the ground beneath your feet, is hurtling through space at over 1,000 miles per hour. And yet, you feel nothing. No wind. No dizziness. No sense of motion at all. The Earth has been spinning beneath you your entire life, and it has never once asked for your permission, your attention, or your awareness. It simply turns. And here's what nobody ever stops to ask. Why? Why is everything spinning? Why does every planet rotate? Why do galaxies turn like slow, ancient carousels? Why do hurricanes spiral? Why do black holes twist space itself? Why do the very atoms inside your body carry a quantum property called spin? From the largest structure in the observable universe, to the smallest particle inside a single cell of your skin, everything is turning. Tonight, we are going to follow that spin. We are going to drift backwards through time, all the way to the beginning, and trace the quiet, invisible thread of rotation that connects the Big Bang to the breath you are taking right now. There is nowhere you need to be. Nothing you need to do. Just listen. And let the universe turn. Before we dive in, subscribe to the channel. It's a small thing for you, but it helps this channel grow. But before we travel to the edge of time, I want to ask you something strange. Have you ever watched water drain from a bathtub? That slow, lazy spiral. That gentle clockwise or counterclockwise curl as it disappears. Most people think that's caused by the Earth's rotation, the famous Coriolis effect. The idea that water drains one way in the northern hemisphere and the other way in the southern. It's one of the most repeated science facts on the internet. And it's mostly a myth. For a bathtub, the forces involved are far too small. The shape of your tub, the way you filled it, which direction you stepped away, those matter far more than the Earth's spin. But here's what's not a myth. That spiraling tendency, that bias toward rotation, is real. It shows up at scales we can barely imagine. And understanding why it exists at all takes us somewhere far more beautiful than a bathtub. It takes us to the very first moments of the universe. 13.8 billion years ago, there was nothing. Not dark nothing. Not quiet nothing. Nothing nothing. No space. No time. No matter. No motion. And then, in an instant that defies every word we have for instant, the universe began. The Big Bang was not an explosion in space. It was space. Space itself expanding, stretching outward in every direction simultaneously, carrying with it the raw, chaotic energy that would eventually become everything you have ever seen, touched, or loved. In those first fractions of a second, the universe was a seething, unimaginably hot soup of energy and particles. Temperatures so extreme that the laws of physics as we understand them today hadn't yet fully settled into place. And within that chaos, something crucial happened. The energy was not perfectly smooth. Tiny quantum fluctuations, variations so small they existed at the level of probability itself, created microscopic differences in density across the newborn universe. Some regions had just slightly more energy than others. Some pockets were just barely more crowded. These were not dramatic differences. We are talking about variations smaller than anything you could ever measure with human instruments. But they mattered infinitely. Because when slightly denser regions began pulling surrounding material inward through gravity, that material didn't fall in perfectly straight lines. It couldn't. Different parts of a collapsing cloud were moving at slightly different speeds, in slightly different directions. The cloud had what physicists call angular momentum, a slight, inherited bias toward rotation baked into it by the randomness of those early quantum fluctuations. And here is the rule that changes everything. Angular momentum is conserved. This is one of the most fundamental laws in all of physics, and it applies everywhere from a spinning ice skater to a collapsing galaxy. What it means, in the simplest possible terms, is this. Once something starts rotating, that rotation doesn't just disappear. It transfers. It concentrates. It speeds up when things collapse inward and slows down when they spread out, but it never vanishes. The rotation in the universe today is the same rotation that was born in those first chaotic moments after the Big Bang. When you watch the Earth turn, when you see Jupiter's storms spiral, when you watch a galaxy pinwheel through the darkness, you are watching echoes. Echoes of the original chaos. The original unevenness. The original quantum trembling of a universe that had just begun. Isn't that something? The spin of the planet beneath you right now can be traced, through an unbroken chain of physics, all the way back to a quantum fluctuation 13.8 billion years ago. You are not just living on a spinning world. You are living on the memory of the Big Bang. Now that we understand where the spinning came from, a question that sounds almost too simple starts to feel genuinely mysterious. Why doesn't it stop? We live in a world full of friction. Bicycle wheels slow down. Spinning tops fall over. Even the most perfectly engineered gyroscope on Earth will eventually, gradually, come to rest. So why has the Earth been spinning for 4.5 billion years? Why hasn't it stopped? The answer is more beautiful than you might expect. And it begins with the one thing that exists between the Earth and the Sun. Absolutely nothing. Space is the most frictionless place in existence. Here on Earth, when something spins, air pushes back. Surfaces grind. Energy leaks away into heat and sound and stillness. But out there? Between the Earth and the Sun stretches approximately 93 million miles of almost perfect nothing. No air molecules to drag against. No surface to catch. No resistance to bleed the energy away. And so the Earth, set spinning by the ancient chaos of the solar system's formation, 4.5 billion years ago, has simply kept going. The same way a spinning top in a vacuum would spin essentially forever, the Earth rotates because there is nothing out there significant enough to stop it. Nothing out there. But something closer to home? That's a different story. Look up on a clear night. The moon. Quiet. Patient. Enormous in its silence. We have looked at it for our entire existence as a species, painted it on cave walls, written poems for it, blamed it for madness and tides and love. It feels like something that simply exists, a passive presence, a beautiful ornament in the night sky. But the moon is not passive. The moon is working. Right now, at this very moment, the moon is reaching across 239,000 miles of empty space and doing something almost imperceptible, almost impossibly slow, and yet completely, measurably real. It is stealing your day. Not dramatically. Not in a way you could ever feel. But the moon's gravity pulls on the Earth, specifically on the oceans, creating the tides we all know and take for granted. High tide, low tide. The rhythmic breathing of the sea. What most people never consider is what those tides do to the Earth's rotation. As the oceans bulge in response to the moon's gravity, as that water piles up and sloshes across the ocean floors and against coastlines, it creates friction. Enormous, planet-scale friction. The ocean tides are essentially a brake pad pressed gently against the spinning Earth. And over millions upon millions of years, that braking adds up. When the Earth was young, freshly formed, still glowing with the heat of its own violent birth, it spun dramatically faster than it does today. A full day on early Earth? 6 hours. Imagine that. The sun would rise, race across a sky that was almost certainly orange and hazy with volcanic ash, and set again, in just 6 hours. You would have 4 sunrises before what we now call noon. The young moon, also much closer to Earth than it is today, was enormous in that early sky, hanging low and heavy, raising tides not of feet, but potentially of hundreds of feet. Walls of water rolling across a planet barely recognizable as our own. And those monster tides break the Earth's spin faster still. Over time, as the Earth slowed, and as the physics of the system balanced out, the moon drifted further away. It is still drifting. Right now, tonight, the moon is moving away from Earth at roughly the same rate your fingernails are growing. About 1.5 inches per year. Small, steady, relentless. And as it drifts further, its braking force weakens. Our days lengthen more slowly. But they are still lengthening. Every single century, the Earth's day grows by approximately 1.4 milliseconds. That sounds like nothing. But 1.4 milliseconds per century, compounded across geological time, is how you get from a 6-hour day to a 24-hour day. The math works. The physics is real. And it points towards something that sounds almost like the plot of a science fiction story. Given enough time, billions upon billions of years from now, the Earth's rotation could slow until it is tidally locked to the moon. Just as the moon already shows us only one face, turning once for every orbit, perfectly synchronized. The Earth could one day turn once for every lunar month. A single day lasting 47 of our current days. One side of the planet in permanent daylight. The other in permanent night. We are nowhere near that future. The sun will likely expand into a red giant and swallow the Earth long before tidal locking fully completes. But the direction of travel is real. The Earth is winding down. Slowly. Gracefully. Unstoppably. Like a music box that was wound 4.5 billion years ago, and is still, barely, still playing. Here is a detail I find quietly wonderful. Scientists can actually measure ancient day lengths, not by guessing, but by reading the rings inside fossilized coral. Coral, like trees, grows in layers, daily layers and annual layers, microscopic rings of calcium built up one day at a time. By counting the daily growth rings between annual markers in ancient coral fossils, paleontologists can calculate exactly how many days were in a year during different periods of Earth's history. Because here's the thing, the year hasn't changed much. Earth's orbital period around the Sun, the time it takes to complete one full journey, has remained relatively stable. But the day has changed dramatically. 400 million years ago, during the Devonian period, when the oceans were full of strange armored fish and the land was just beginning to be claimed by the first forests. A year on Earth had approximately 400 days. Not because the year was longer, but because the days were shorter. The Earth was spinning faster. The dinosaurs, those magnificent, planet-dominating creatures who ruled for 165 million years, lived under a sun that rose and set a little faster than ours. Their days were slightly shorter. Not dramatically, perhaps 23 hours instead of 24 at certain points. But measurably, provably shorter. When a brachiosaurus stretched its long neck toward the treetops in the afternoon light. That afternoon was not quite the same length as yours. There is something deeply moving about that. The idea that the length of a day, something so fundamental, so woven into every rhythm of life, is not fixed, is not permanent, is just another number the universe is slowly, patiently changing. And we can read that change. In coral. In stone. in the patient record that the Earth keeps of its own slowing heartbeat. Now, while we're here, spinning gently with the Earth, there is something else worth knowing. The Earth does not spin in a perfectly straight, stable, upright line. It wobbles. Like a top that has been spinning for a very long time and is just beginning, just barely, to feel the effects of its own imperfection. The Earth is tilted at approximately 23.5 degrees relative to its orbital path around the Sun. This tilt, this gorgeous, life-giving lean, is what gives us seasons. It is why summer exists. Why winter comes. Why the midnight sun shines over the Arctic and why some nights in Antarctica stretch on for months. But that tilt itself is not fixed. Over a cycle of approximately 41,000 years, the Earth's axial tilt slowly shifts, between roughly 22 degrees and 24.5 degrees. A gentle nodding, back and forth, across timescales that dwarf all of human civilization. And then there is the precession. The slow, circular wobble of the Earth's axis itself, like a gyroscope gradually tracing a circle in the sky. One complete precession cycle takes approximately 26,000 years. And here is why that matters. Right now, the Earth's northern axis points toward a star we call Polaris. The North Star. The fixed point that navigators have used for thousands of years. But Polaris will not always be the North Star. 5,000 years ago, when the ancient Egyptians were building the pyramids, the pole star was a different star entirely. A star called Thuban, in the constellation Draco. In another 12,000 years or so, the pole star will be Vega, one of the brightest stars in the summer sky. The night sky itself is slowly rotating above us. And the Earth, without anyone noticing, without any fanfare, is slowly rewriting which star gets to be called the center of the heavens. We think of the Earth as stable, as the ground beneath us, the fixed thing. But nothing is fixed. Everything is in motion. Everything is, in its own way, spinning. So we have our answer, in part. The Earth spins because angular momentum, born in the chaos of the early solar system, has never had anywhere to go. Space offers no friction, no resistance, no reason to stop. It slows only because the moon reaches across the void and presses, gently, against the ocean tides. A process so slow it takes millions of years to shave a single hour from our day. And it wobbles, tilts and nods and precesses, because the Earth is not a perfect sphere, and the gravity of the sun and moon never quite pulls on it in a perfectly symmetrical way. Spin. Slow. Wobble. The quiet, endless mechanics of our world. But now, I want to take you somewhere larger. Because if you think the Earth's rotation is remarkable, wait until you see what a galaxy does. 100 billion stars, held together not just by gravity, but by something we cannot see, cannot measure directly, and do not fully understand. Something we call dark matter. And without it, galaxies shouldn't spin the way they do. In fact, without it, they shouldn't exist at all. Let me paint you a picture. Imagine a record player. An old one. Vinyl. The kind that spins with a low, satisfying hum. Now imagine placing a coin near the center of that spinning record, and another coin near the outer edge. Watch them carefully. The coin near the center moves in tight, fast circles. The coin near the edge traces a much wider, slower arc. This is exactly what we would expect from basic physics, from the same laws that govern planets orbiting the Sun. Things closer to the center of a rotating system move faster. Things further out move slower. Mercury orbits the Sun faster than Neptune. A figure skater spins faster when they pull their arms in. This is not an opinion. This is not a theory. This is a law. And galaxies? Completely ignore it. In the 1970s, an astronomer named Vera Rubin sat in her observatory and measured something that should have been straightforward. She was mapping the rotation of the Andromeda galaxy, our nearest large galactic neighbor, a swirling island of roughly 1 trillion stars suspended 2.5 million light-years away. Her method was elegant and well established. By measuring the Doppler shift of light from different parts of the galaxy, the way light stretches slightly redder when a star moves away from you, and slightly bluer when it moves toward you, she could calculate exactly how fast different parts of the galaxy were rotating. She expected to see the record player pattern. Stars near the bright, dense galactic center, spinning fast. Stars near the dark, sparse outer edges, spinning slow. A smooth, predictable curve. Textbook physics. What she found instead stopped her cold. The outer stars were spinning just as fast as the inner ones. Not slightly off. Not a minor discrepancy to be explained away by measurement error. Wildly, dramatically, impossibly fast. By every law of physics available to her, those outer stars should have been flung into the void billions of years ago. There simply wasn't enough visible matter, enough stars and gas and dust, to generate the gravitational pull needed to hold them in their orbits at those speeds. The galaxy should have torn itself apart. And yet there it was. Spinning. Intact. Graceful and whole and utterly indifferent to the confusion of the human beings staring up at it. Vera Rubin did not panic. She did not dismiss her own data. She looked at the numbers carefully, checked them again, and arrived at a conclusion that was both deeply simple and cosmically staggering. There must be more mass out there. Mass we cannot see. Mass that produces no light, reflects no light, absorbs no light, invisible to every telescope ever built, and yet gravitationally real. Gravitationally present. Gravitationally holding the outer arms of the galaxy in their orbits the way an invisible hand might hold the edge of a spinning top. She called it, with characteristic restraint, a discrepancy. The rest of the scientific community, over the following decades, arrived at a name that has since become one of the most famous, and most mysterious, phrases in all of science. Dark matter. Let's be honest about something. We do not know what dark matter is. That is not a failure. That is not an embarrassment. That is science at its most raw and most beautiful, staring at an observation it cannot explain and refusing to look away. What we do know is this. Dark matter is not dark in the poetic sense. It is not a shadowy, sinister thing lurking between the stars. It is simply invisible. It does not emit light the way stars do. It does not reflect light the way planets do. It does not absorb light the way black holes and dust clouds do. It interacts with the electromagnetic force, the force that governs light, in essentially no way at all. To light, dark matter is a ghost. To gravity, it is as real as anything else in the universe. And there appears to be an enormous amount of it. Current estimates, built from decades of observational data, gravitational lensing studies, cosmic microwave background measurements, and galactic rotation curves like Vera Rubin's, suggest that dark matter makes up approximately 27% of the total mass-energy content of the universe. Ordinary matter, everything you can see, touch, measure, and name, the stars and planets and gas clouds and galaxies and every atom in your body, makes up only about 5%. 5%. The universe you can observe, in all its staggering vastness, all its billions of galaxies each containing billions of stars, is just the visible fringe. The lit edges of something far, far larger and stranger. The remaining 68%, by the way, is something even more mysterious, something called dark energy, which is driving the expansion of the universe and accelerating it. But that is a story for another night. Tonight, we stay with the spin. And what dark matter tells us about spinning galaxies is something almost poetic in its simplicity. Galaxies spin the way they do because they are embedded in something we cannot see. Like a visible top spinning inside an invisible bowl. The dark matter forms an enormous, roughly spherical halo around each galaxy, extending far beyond the visible stars, far beyond the bright galactic disk, out into the dark and empty space that surrounds it. And it is this halo, this invisible gravitational scaffolding, that provides the extra pull. That keeps the outer stars locked in their orbits. That holds the spiral arms together across billions of years of rotation. Without dark matter halos, galaxies as we know them would not exist. The Milky Way would not exist. The solar system, born in one of the Milky Way's spiral arms, would not exist. You would not exist. The invisible holds the visible together. Let's come a little closer to home. Our own galaxy, the Milky Way, is a barred spiral galaxy. A vast, flattened disk of somewhere between 100 and 400 billion stars, with two major spiral arms and a dense, glowing bar of stars crossing its center. It is approximately 100,000 light-years across. If you tried to drive across it in a car traveling at highway speed, 60 miles per hour, the journey would take approximately 1 trillion years. The universe is only 13.8 billion years old. You would need to have started driving roughly 70 universes ago. This is the scale we are talking about. And this entire structure, all 100,000 light-years of it, is rotating. Our solar system sits roughly 26,000 light-years from the galactic center, about halfway out, nestled between the spiral arms. And we are moving, right now, at approximately 514,000 miles per hour around the center of the galaxy. That is fast enough to cross the entire United States in about 20 seconds. And yet, one complete orbit of the Milky Way takes our solar system approximately 225 to 250 million years. We call this unit of time a galactic year. Or sometimes, a cosmic year. And when you measure Earth's history in galactic years, history becomes something entirely different. The dinosaurs went extinct approximately 1 galactic year ago. The first complex animals on Earth, the creatures of the Cambrian explosion, with their eyes and shells and strange, alien body plans, appeared roughly 2 galactic years ago. The Earth itself is only about 20 galactic years old. The Sun has completed perhaps 20 to 25 laps around the Milky Way since it first ignited. In the next galactic year, the next 225 million years or so, the continents will have rearranged themselves beyond recognition. Species alive today will be replaced by creatures we cannot imagine. Mountain ranges will rise and erode. Oceans will shift. And the solar system will complete one more quiet, unhurried loop around the galactic center. As it has done. As it will do. While we are here, in the Milky Way, spinning gently around the galactic center. There is one more thing worth pausing on. The spiral arms. Those long, graceful curves of stars and gas and dust that give spiral galaxies their breathtaking shape, the shape that fills astronomy photographs with such luminous, sweeping beauty. You might assume that the spiral arms are fixed structures, permanent features of the galaxy, that the stars within them simply belong there, rotating with the arm like spokes of a wheel. But they are not. The spiral arms of a galaxy are not made of specific stars. They are more like a traffic jam. Imagine a highway with a slow-moving bottleneck. Cars back up behind it. From above, you see a dense cluster of vehicles, a distinct, visible structure on the road. But it is not the same cars that form the traffic jam. Cars enter from behind, slow down, move through, and exit out the front. The jam persists even as the individual cars keep moving. Spiral arms work the same way. They are density waves, regions of slightly higher gravitational pressure that move through the galactic disk more slowly than the individual stars themselves. Stars enter the arm, slow down slightly in the denser region, and then drift through and out the other side. What you see in those gorgeous galaxy photographs, those sweeping, luminous arms, is not a fixed structure. It is a pattern. A wave moving through a sea of stars. A ripple of gravity, 100,000 light-years wide, that has been propagating through the Milky Way since before our solar system existed. And inside that pattern, inside that slow-moving gravitational density wave, stars are compressed. Gas clouds collapse. New stars are born. The spiral arms of galaxies are stellar nurseries. The regions where gravity gently squeezes the raw ingredients of stars and planets and, eventually, life, into existence. Our solar system was likely born inside a spiral arm. We have since drifted out of it. But the arm is still there. Still turning. Still compressing gas into new stars that will burn long after our own sun has faded. The spin of the galaxy is not just beautiful. It is generative. It creates. So we have traveled far tonight. From the quantum trembling of the early universe, to the breaking pull of the moon on our oceans, to the invisible dark matter scaffolding that holds entire galaxies together. Spin, at every scale, has turned out to be not just a curiosity, but a necessity. The organizing principle of the cosmos. But here is where the story takes its strangest turn yet. Because we have been talking about spin as something that objects do. Planets spin. Galaxies spin. Particles spin. But Albert Einstein, quietly, methodically, in the language of pure mathematics, showed us something that should be impossible. Space itself can spin. Not the things inside space. Not the matter moving through space. The fabric of space and time, the very stage on which all of reality performs, can be twisted, dragged into rotation by a massive spinning object. Like a bowling ball placed on a rubber sheet, but rotating. Slowly winding the sheet around itself. We call this effect frame dragging. And we have measured it. Not in theory. Not in simulation. In real, observable, measurable reality. Coming up, we follow Einstein into the deepest, strangest consequence of a spinning universe. Where even time gets twisted. And where the most extreme spinning objects in existence, objects so dense that a teaspoon of their material weighs 1 billion tons, drag the universe itself around with them as they turn. There is a thought experiment I want you to try. Close your eyes for a moment, or simply let them rest, soft and unfocused, on whatever is in front of you. Imagine a still pond. No wind. No ripples. Perfectly flat. Perfectly calm. Now imagine dropping a stone into the center of that pond. Ripples spread outward in perfect circles, concentric rings moving away from the point of impact at a steady, predictable speed. Now imagine something different. Instead of dropping a stone, you drop a spinning stone. One that rotates rapidly as it sinks through the water. Watch what happens to the ripples. They don't just spread outward anymore. They twist. They spiral slightly, pulled around by the rotation of the stone, carrying that rotational information outward in every direction. The water itself, the medium, has been affected by the spin. Now replace the pond with spacetime. Replace the stone with a massive, rapidly rotating object, a planet, a star, a black hole. And ask yourself what happens to the fabric of reality when something that heavy spins. In 1915, Albert Einstein published his general theory of relativity. It was, and remains, one of the most breathtaking intellectual achievements in human history. Before Einstein, space was a stage. A fixed, neutral, unchanging backdrop against which the drama of the universe played out. Matter moved through space. Time passed within space. But space itself was just there. Passive. Indifferent. Empty. Einstein looked at this picture and said, quietly but firmly, "No. Space and time are not a stage. They are not a backdrop. They are not separate, fixed, passive things. Space and time are a single, unified fabric, what Einstein called spacetime. And that fabric is not rigid. It bends. It curves. It stretches and compresses in response to mass and energy. A massive object like the sun doesn't just sit in space, it warps the spacetime around it, creating a curved geometry that we experience as gravity. The Earth doesn't orbit the sun because some invisible force reaches out and pulls it. The Earth follows the curved shape of spacetime, like a marble rolling around the inside of a bowl. This was revolutionary enough on its own. But Einstein and the physicists who followed him soon realized the theory implied something even stranger. If a massive object curves spacetime by simply existing, what does it do to spacetime when it rotates? The answer came in 1918, just 3 years after general relativity, when Austrian physicists Joseph Lenz and Hans Thüring worked through the mathematics and found something extraordinary. A rotating massive object doesn't just curve the spacetime around it. It drags it. Like a spinning ball submerged in honey, the ball's rotation pulls the honey around with it, creating a slow, circular current in the surrounding medium. A spinning massive object pulls the very fabric of spacetime into rotation around itself. This effect has a name: frame dragging. Or, more formally and more beautifully, the Lenz-Thüring effect. And it means this. Near a rotating massive object, the reference frame of space itself, the coordinate system of reality, is being slowly twisted and dragged in the direction of rotation. If you were floating in space near a rapidly rotating massive object and tried to point in a perfectly fixed direction, you couldn't. Because the space you are pointing through is rotating around you. The universe itself is pulling your finger around. Frame dragging sounds like something from a science fiction novel, which is perhaps why it took nearly a century to prove it experimentally. In April 2004, NASA launched a spacecraft called Gravity Probe B. It was one of the most precise scientific instruments ever built. Inside it, for gyroscopes, spheres of quartz so perfectly round that if you scaled them up to the size of the Earth, the tallest mountain on their surface would be just 8 feet tall. Perfectly, almost impossibly spherical. These gyroscopes were set spinning in the frictionless vacuum of space and pointed toward a distant guide star, IM Pegasi, as a fixed reference point. The mission was simple in concept and staggering in execution. If Einstein was right, if the Earth's rotation was dragging the spacetime around it, then the axes of those perfect gyroscopes should drift over time. Should be slowly, measurably pulled out of alignment by the twisted fabric of space surrounding our rotating planet. The spacecraft spent 17 months in orbit, collecting data. Then another 5 years analyzing it, working through the noise, the systematic errors, the almost incomprehensible precision required to measure an effect this small. The expected drift from frame dragging? 0.000011 degrees per year. 11 thousandths of 1,000th of a degree per year. For context, if you blinked, And that blink shifted your line of sight by the tiniest fraction of a degree. Frame dragging is roughly 50,000 times smaller than that. And they measured it. Not approximately. Not within a vague margin. But precisely, definitively, in exact agreement with Einstein's predictions. Frame dragging is real. The Earth is pulling spacetime around with it as it rotates. Right now. Silently. Imperceptibly. The ground beneath your feet is not just spinning through space. It is twisting space itself. The Earth's frame dragging effect is real but vanishingly small. To see frame dragging at scales that genuinely warp the imagination, we need to visit the most extreme rotating objects in the universe. We need to talk about pulsars. When a massive star, much larger than our Sun, reaches the end of its life, it explodes in a supernova. A cataclysm so bright it can briefly outshine an entire galaxy of 100 billion stars. What remains at the center of that explosion, if the star was the right size, is something almost impossible to fully visualize. A neutron star. The core of the original star, compressed by the violence of the explosion into a sphere roughly 12 to 15 miles across. To put that in perspective, the Sun, if compressed to neutron star density, would fit inside a sphere roughly the size of a city. All of that mass, all of that gravity, packed into something you could theoretically drive across in 20 minutes. At neutron star densities, matter as we know it ceases to exist. Individual atoms are crushed. Electrons are forced into protons to create neutrons. The entire object becomes, in essence, a single gigantic atomic nucleus, held up not by ordinary pressure, but by quantum mechanical forces that operate at the level of subatomic particles. A single teaspoon of neutron star material would weigh approximately 1 billion tons. Place that teaspoon on a scale on Earth, and the scale, along with the Earth beneath it, would be in serious trouble. Now here is where spin enters the picture. The original star, before it exploded, was rotating. Slowly, perhaps once every few weeks or months. But as the supernova explosion compressed the core, as that city-sized remnant collapsed from something the size of the Sun to something the size of a small city, angular momentum was conserved. All that rotation, concentrated into a fraction of the original volume. The result? Some neutron stars spin hundreds of times per second. Not hundreds of times per minute. Per second. The fastest known pulsar, PSR J1748-2446 AD, rotates 716 times every single second. 716 complete rotations. Per second. At its equator, the surface of that neutron star is moving at approximately 24% of the speed of light. A quarter of the speed of light. At the surface of a star. And pulsars announce themselves. As a neutron star rotates, it sweeps powerful beams of electromagnetic radiation, radio waves, X-rays, gamma rays, out into space like a lighthouse beam sweeping across the darkness. Each time that beam sweeps past Earth, our telescopes detect a pulse. 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 Arriving with a regularity so precise that when the first pulsar was discovered in 1967 by astronomer Jocelyn Bell Burnell, her team briefly, only half-jokingly, designated it LGM-1. Little green men. Because nothing natural, they assumed, could produce a signal that perfectly regular. But nature could. And does. Pulsars are, in some respects, the most precise clocks in the universe. Some keep time to an accuracy that rivals, and in some cases surpasses, the best atomic clocks on Earth. The universe, in its most extreme environments, produces rotating objects so perfectly consistent that they function as cosmic timepieces. Spin so regular it looks like intention. If pulsars represent extreme spin, black holes represent something beyond our ability to fully describe. Particularly rotating black holes. In 1963, mathematician Roy Kerr solved Einstein's field equations for a rotating mass, and found a solution that revealed something physicists had not anticipated. Around a rotating black hole, frame dragging doesn't just gently nudge the fabric of spacetime. It dominates it completely. A rotating black hole creates a region around itself, outside the event horizon, the point of no return, called the ergosphere. Inside the ergosphere, frame dragging is so extreme that it becomes literally impossible to remain stationary relative to the distant universe. Space itself is flowing, rotating, faster than anything can move to counteract it. To remain stationary inside the ergosphere would require moving faster than light in the opposite direction. And since nothing moves faster than light, stationary is not an option. Everything inside the ergosphere, every particle, every photon of light, every unit of space itself, is being carried around with the rotation of the black hole. You cannot stop spinning. The universe won't let you. There is something philosophically vertiginous about this. We began this journey with the observation that you are spinning right now, on a rotating Earth, moving through a rotating galaxy, in a universe full of spinning things. But the ergosphere of a rotating black hole tells us that spin is not just something that happens in the universe. Near its most extreme expressions, spin is the universe. It is the structure of spacetime itself. The thing that cannot be escaped, cannot be stopped, cannot be separated from the fabric of reality. Before we leave this territory, this strange, twisted landscape where space itself rotates, there is one more spin worth mentioning. The smallest one of all. Inside every atom in your body, inside the electrons orbiting their nuclei, inside the protons and neutrons packed into those nuclei, inside the quarks that make up those protons and neutrons, there is a property called spin. Quantum spin. And here is where language reaches its limit, because quantum spin is not actually rotation in the physical sense. An electron does not literally rotate like a tiny Earth on a tiny axis. If you tried to model it that way, the math breaks down almost immediately. Quantum spin is something else entirely, an intrinsic, fundamental property of particles. As fundamental as their mass or their electric charge. It simply is. And yet we call it spin because it behaves in ways that are mathematically analogous to angular momentum. Because it produces magnetic effects, just as rotating charges do. Because the universe, from its largest scales to its smallest, seems to have organized itself around a concept that is, at its heart, rotational. Physicists use the word spin at the quantum scale not because they understand exactly what it is, but because spin is the closest word we have for something the universe does at every level. Something so fundamental it shows up in the mathematics of reality itself. From the quantum trembling of a subatomic particle, to the slow, majestic rotation of a galaxy cluster spanning hundreds of millions of light years. The universe does not just contain spin. The universe speaks in spin. It is the language the cosmos chose, in the first moments of its existence, and has never stopped using. We have come a long way tonight. From the quantum fluctuations of the Big Bang, to the moon pressing gently against our oceans, to dark matter halos holding galaxies together, to Einstein's twisted spacetime, to pulsars spinning 716 times per second, to black holes that make stationary impossible. Spin, at every scale, at every level of reality, has turned out to be not an accident, but an architecture, the hidden structure beneath everything. And now, at last, I want to ask the question that has been waiting quietly at the edge of this whole journey. What happens if it stops? Not just the Earth's rotation, not just the galaxy. What if, in some far, unimaginable future, the great turning of the cosmos wound down to stillness? What would a universe without spin look like? And is there, hidden inside that question, something that tells us not just about the future, but about why we are here at all? Part 5 is the quiet one. The ending. The place where science and something that feels almost like wonder become, for just a moment, the same thing. Settle in. We are almost home. There is a specific kind of quiet that only exists after something has been spinning for a very long time. You have felt it, maybe, without ever naming it. The moment a fan blade slows to stillness after you turn it off. The last wobble of a coin settling flat on a table. The final, barely perceptible trembling of a spinning top. Right before it tips, rests, stops. There is something unexpectedly moving about that moment. Not sad, exactly. Just complete. And tonight, before we let the universe carry you gently toward sleep, I want to sit with you at the edge of the largest version of that moment imaginable. The moment, impossibly far away, perhaps never truly arriving, when the last spinning thing in the universe finally rests. Let us be honest about something, first. The universe is not slowing down uniformly. It is not winding toward stillness the way a clock winds toward midnight. The universe is expanding, accelerating in its expansion, driven by that mysterious dark energy we mentioned in Part 3. Galaxies are not drifting gently toward rest. They are hurtling away from each other, faster and faster, into an increasingly cold and empty darkness. So the question, what happens if everything stops spinning, is not quite as simple as it sounds. But let us follow it anyway. Because the thought experiment reveals something beautiful. Imagine, first, what a non-spinning Earth would look like. We actually have reasonable data on this, because we know what happens to planets that have been tidally locked, planets that have, over billions of years, been braked to the point where they no longer rotate relative to their star. Mercury, the closest planet to the Sun, is not quite tidally locked but rotates so slowly that a single day on Mercury lasts approximately 59 Earth days. The Moon is tidally locked to Earth, which is why we always see the same face. The far side of the Moon, the dark side, in the sense of unknown, unseen, has never been visible from Earth with the naked eye in all of human history. Now imagine the Earth tidally locked to the Sun. One face in permanent daylight. Blazing. Relentless. Temperatures that would eventually strip the atmosphere from the sunward side, boiling the oceans into space one molecule at a time. The other face in permanent night. Cold beyond anything currently experienced on Earth's surface. Temperatures plunging toward the point where the remaining atmosphere would freeze and snow down onto the dark ground in a slow, silent precipitation of solid nitrogen and oxygen. Between these two extremes, a narrow ring of perpetual twilight. A Terminator line, a border between fire and ice, perhaps the only place where temperatures would remain within ranges that liquid water, and therefore life, might survive. A thin, curved sliver of habitable twilight. The last livable edge of a stopped world. It is a haunting image. A world that has forgotten how to spin. A world where the sunrise that has greeted every morning of every living thing that has ever existed on this planet simply never comes. Because it already arrived. And it never left. Now zoom out further. What would stop a galaxy from spinning? In principle, friction. But as we established in Part 2, space offers almost none. In practice, nothing, on any timescale we can meaningfully imagine. The Milky Way has been rotating for approximately 13 billion years. It will continue rotating for billions more. Even as stars die and are not replaced. Even as the stellar population of the galaxy ages and dims. Even as the last red dwarf stars, the smallest, dimmest, most miserly consumers of hydrogen fuel, burn down to cold, dark cinders over timescales of 10 trillion years. 10 trillion years. The current age of the universe is 13.8 billion years. 1 trillion is roughly 70 times that. 10 trillion is 700 times the current age of the universe. And red dwarfs will still be burning. The galaxy, in some form, some sparse, cold, dimming shadow of its current luminous self, will still be turning. But even red dwarfs die eventually. And what comes after, in the deepest future that physics allows us to imagine, is a darkness and a stillness that strains the very concept of time. The era physicists call the degenerate era, spanning from roughly 10 trillion to perhaps 10 to the power of 40 years from now, is a universe of stellar corpses. White dwarfs cooling to black dwarfs. Neutron stars still spinning, still pulsing, but with no new energy source, gradually radiating their heat into an increasingly cold cosmos. Even black holes, those ultimate spinning objects, those frame-dragging monsters we visited in Part 4, eventually evaporate. Stephen Hawking showed us this in 1974. Black holes are not truly black. They emit a faint, quantum mechanical radiation, Hawking radiation, and over unimaginable timescales, they slowly, particle by particle, lose their mass. The largest black holes in the universe, the supermassive giants at the centers of galaxies, with masses billions of times that of our Sun, will take approximately 10 to the power of 100 years to fully evaporate. That number, 10 to the 100th power, has a name. A googol. The word that eventually inspired the name of the search engine you likely use today. After a googol of years, the last black holes will be gone. The last rotating objects of any significant mass will have evaporated into a thin, cold, diffuse soup of fundamental particles, spread so thinly across a universe so vast that the average distance between particles will be larger than the current observable universe. No stars. No planets. No pulsars. No black holes. No spin. Just particles. Drifting. Cooling. Approaching, but never quite reaching, absolute zero. The physicists call this state the heat death of the universe. The moment of maximum entropy. Where nothing gradients remain. Where no temperature differences exist to drive any process. Where no rotation exists to organize matter into structures. Where the universe, at last, after a story of almost incomprehensible length and complexity, goes still. I want to be careful here. Because it would be easy to hear that image, the heat death, the final stillness, the googol of years, and feel something like despair. The universe winding down. The last spin ending. Everything going cold and dark and motionless forever. But I think that reading misses something essential. Something that the physics itself is quietly trying to tell us. Consider what it took to produce this moment. Right now, this moment, as you listen, as you breathe, as your chest rises and falls with the effortless rhythm of a body that has never had to think about breathing. The universe is at its most complex. 13.8 billion years of gravitational sculpting. Of gas clouds collapsing into stars. of stars forging heavy elements in their cores and scattering them across space in their depths, of those elements assembling, on at least one small rocky world, into chemistry, and of that chemistry folding itself, over billions of years, into biology, into cells, into nervous systems, into brains, into consciousness, into you, lying here, in the dark, on a spinning planet, listening to a story about spinning planets. The universe required a googol of years to wind down to stillness. But it only required 13.8 billion to produce something capable of wondering about it. That asymmetry is not nothing. That asymmetry is, arguably, everything. The spin of the universe produced us. The angular momentum born in the chaos of the Big Bang, conserved across billions of years, concentrated into gas clouds, into stars, into a solar system, into a planet at exactly the right distance from exactly the right star. Produced the conditions for water, for warmth, for the long, patient unfolding of life. The spin of the galaxy carried our solar system through the right neighborhood, at the right time, through the right density waves, sparking the right chemistry. The spin of the Earth gave us day and night, the rhythm that life learned to breathe with, that plants learned to track, that every circadian clock in every living cell on this planet is tuned to. The spin of the moon stabilized our axial tilt, keeping our seasons regular enough, our climate stable enough, for complex life to take hold and not be wiped out by the wild temperature swings that would come from a wobbling, precessing planet with no massive moon to hold it steady. Remove any one of these spins, and this moment doesn't exist. This story doesn't exist. You don't exist. So here we are, at the end of the spinning. Or rather, at the end of our small journey through it. The universe outside is still turning. Will still be turning long after every story ever told has been forgotten. Long after the sun has expanded and cooled and the earth has been consumed and the last light in the Milky Way has gone out. It will turn in the darkness. In the cold. In the long, patient waiting of a cosmos that has forgotten it was ever bright. But right now it is spinning and warm and luminous and alive. Right now a star called the Sun is burning 93 million miles away, fusing hydrogen into helium, pouring light across a solar system that is moving at 500,000 miles per hour around a galaxy that has been turning for 13 billion years. Right now the moon is drifting, imperceptibly, but measurably, an inch and a half further from the Earth than it was a year ago, pressing gently against the tides, lengthening your day by 1.4 milliseconds per century. Right now pulsars are sweeping their lighthouse beams across the galaxy, pulse, 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 keeping cosmic time with an accuracy that humbles our finest clocks. Right now a rotating black hole somewhere in the darkness is dragging spacetime around with it, twisting the fabric of reality into slow, majestic spirals that no human eye will ever see. And right now, your body, your atoms, every proton and electron and quark in every cell of your resting, breathing, beautiful body, is spinning. Not metaphorically, not poetically, physically, with the same angular momentum that was seeded into the universe in the first fraction of the first second of existence. You are not separate from the spinning universe. You are not an observer of it. You are made of it. Every rotation, every orbit, every slow galactic turn has been building, across 13.8 billion years, toward the improbable, unrepeatable, quietly astonishing fact of you. Lying here. Breathing. Listening. Wondering. So let it turn. Let the earth spin beneath you, as it has for 4.5 billion years, carrying you through the night toward a morning that will come whether you wait for it or not. Let the galaxy turn, its 100 billion stars tracing their slow, magnificent arcs around a center you will never see, carrying your solar system on one more small increment of its 225 million-year journey. Let the universe expand and cool and do whatever it will do across its unimaginable future. Because that is not your night. This is your night. This breath. This quiet. This particular darkness on this particular spinning world in this particular moment of a 13.8 billion year story. Rest in it. Turn with it. Let it carry you.